Hello everyone, my name is Matthew McKenzie. I am a fourth year chemical engineering student at the University of Cincinnati, and today I'm going to be doing the first part of the final exam for Transport 2 mass transfer. So this problem deals with differential equations and cooling tower. So the situation: a 10-meter tall cooling tower with 100 meters squared cross-section area has diagonal slats which flowing water comes into contact with counterflowing air. The diagonal slats provide 5 centimeters squared water-air contact area per cubic meter with negligible drop in air pressure. The heat transfer from air to water film flowing down from the diagonal slats of the cooling tower is governed well by this equation here, or correlated well, excuse me. The Nusselt number equals 0.6 times the Reynolds number to the half power times the Prandtl number to the third power. So 50 kilograms of water is fed to the top of the tower at 70 degrees Celsius, and air is fed at a superficial velocity of 5 meters per second, at which exits the top of the tower at 40 degrees Celsius and 90% relative humidity. Under these conditions, the air and water heat transfer coefficient is measured to be 10 watts per meter squared Kelvin. And for simplicity, we can assume that the Lewis number is equal to 1. And so the goal of this part is to derive and explain the differential equations governing the air temperature, water temperature, and water mole fraction in the air. So now these differential equations, they always have some form, d over dz, and then some unit here. And that unit's going to be one of those three values there: the water temperature, air temperature, as well as water mole fraction. So in order to do this, our strategy, we're going to do two energy balances. That will give us the change in air temperature over change in position and change in water temperature over change in position. And we're also going to perform one material balance, or I'm just going to call it a mass balance. This mass balance is going to give us the change in water mole fraction over the change in position. So, in order to actually begin this, what we're going to end up doing, we're going to draw up what's called a baby control volume. So this baby control volume basically tells us what is going into the system and what is exiting the system. So, with what's happening here going into this control volume, we've got the temperature of water and the enthalpy of water. Exiting, we have some air. We're going to call the length of this differential baby control volume dz, and our positive z is downward. That's very important. We've got water exiting, we've got air entering at some temperature, and as well as having some mole fraction of water. So then for another diagram we're going to draw up, we've got this interface where we've got water and air. And at this interface, you've got the concentration of water at the interface, in addition to having the bulk concentration of water in the air. So first thing we're going to do, we're going to write out a material balance for water. Water energy balance. So this water is being cooled. So now with this energy, in always equals out. That is always the case for energy balances for really any quantity. And what we basically have here is the liquid water's change in enthalpy, which we'll call delta H, is equal to the convective heat loss from that water. Because remember, right, it's being evaporated. If there's evaporation happening, that means there's convectively a loss in temperature with the evaporative heat gain. As it's getting energy from the air. Now what that looks like in terms of equations. So first we need to go back up to this second spot here where we're going to write out our superficial mass flow rate for water coming in. So a superficial mass flow rate, well, we can describe as either G, L, or S for some kind of flow rate of material. So here we've got liquid water is equal to the mass flow rate of water over the area, which is that cross-sectional area of 100 meters squared we talked about earlier. This gives us 0.5 kilograms times seconds, -1 times meters to the -2. This allows us to better calculate what the final result would be. So what we've got over here, we've got that superficial mass flow rate of water times the area times the cross-sectional area times the heat capacity of water times some differential temperature change of, excuse me, that should be differential temperature change of water. What that looks like over here, this is basically a mass flow rate of sorts, times your heat capacity times your differential change in temperature. This guy is some differential change in enthalpy. Now we've got to add up the convective heat loss and evaporative heat gain for the water here. So what that looks like is, first we need to write out some kind of area formula. As recall, we're basically writing out something very similar to one of the heat equations where we've got Q equals H times delta T. We're going to be writing out, QAH delta T. We first got to write out our somewhat area component. What's this area component look like? So the first thing we've got some kind of volume here, which is A times dz. This guy is basically just a differential volume in another sense. You can multiply that by the ratio of surface area to volume, which that gives us surface area that we're working with here. So this guy, in a sense, is our area for transferred materials. So the first component we've got convective heat loss, which that's a gain, so therefore that's going to be positive. We've got H times the temperature of air minus the temperature of water. Now this component here is convective heat loss. So the water, as it flows down the tower, is losing energy. But then the water also gains energy from being evaporated. So what that looks like, we've got minus the heat of evaporation times the convective mass transfer coefficient times the difference in concentration between the interface and bulk, which, recall right here, it's just concentration of water at the interface minus the concentration of water at the bulk position. Let's see, this component here is just evaporative mass transfer. And multiply that by lambda, which is our heat of vaporization. That turns into evaporative heat gain. Now, if you take a look over here, our water is going to be cooled down. Therefore, our T delta W is going to be less than 0. This convective loss, this is going to be a positive number. I'm sorry, that's drawn incorrectly. And over here, since the evaporative is going to be, we need essentially this component here to be the same sign as this component. In order to do that, we need to have a negative sign in front, because the concentration of water at the interface is actually greater than that of the concentration of the bulk. So that's how we get our signs there. Okay, and this is our first differential equation. So first diffie-Q check. So moving on to the next part. Now you've got to do an energy balance on air, which, let's see, that's step 6, so this is step 7. So now we're going to be doing is an air energy balance. The air warms up. So within this, you've also got in equals out. You always have to have material going in as the same material going in as the same material going out, because energy and matter cannot be created or destroyed. And in more general terms, this equation is the change in enthalpy of air equals the convective heat gain of air. And what this looks like, it's a very similar equation to the one we worked with before with the water energy balance. So what we've got is the superficial mass flow rate of air and water, just this big G here. It's relatively similar to LW in terms of form if you take a look. Instead of liquid, this guy's gas. Multiply that times the area. This gives us basically a mass flow rate times the heat capacity of air times the differential change in temperature of air across that control volume equals AdZ, which again, this is our volume just like before, times the surface area volume conversion factor, which that gives us an area, multiplied by our convective heat gain component, which would be the heat transfer coefficient times the air temperature minus the water temperature. And this guy is convective heat gain. Alrighty, so this is our second differential equation because now we've got the energy balance for air, which really is just the simple enthalpy change of air is equal to the convective heat gain of that air. So second diff EQ, good. Alrighty, and the third one. Now this third one, we're going to be doing a water material balance. So with the water material balance, again, in equals out, always. And what we've got here is that the change in molar flow rate of air equals the mass transfer of water evaporated. Water evaporation mass transfer. Now, what does this look like in some form of equation? So first, again, we've got to write out some form of mass flow rate, which we can do as the overall gaseous flow rate times the area. This gives us a mass flow rate. Then times the change in mole fraction of water. Now, with this, we've got a mass flow rate times the differential change in mole fraction. That basically is useless to us. So in order to change that to what we need it to, we just divide by the average molecular weight. We divide by the average molecular weight. So this basically converts this. That converts that to a molar flow rate and a mole fraction we can work with. That's all that's doing. And this guy is equal to the negative of the volume. Again, this is the volume. Times our area, times our surface area volume conversion, which this gives us an area. Then finally multiplied by the convective mass transfer for evaporation, which would be the convective mass transfer coefficient times the concentration of water at the interface minus the concentration of water at the bulk position. Well, this component is just evaporative transfer, or evaporative mass transfer. So at this point, we've obtained all our differential equations. However, we're not exactly done yet, because you can't just shove this into a computer right now. We've actually got a few unknown quantities. So unknown quantities. We've got the concentration of water at the interface is unknown. Concentration of water at the bulk is unknown. We don't know what the convective mass transfer coefficient is. We don't know what the average molecular weight is, and we do not know what the overall superficial mass flow rate of the vapor is. So we're going to have to calculate each of these by a few other calculations. So first what we'll do is we'll calculate the concentration of water at the interface and concentration of water at the bulk. So concentration of water at the interface. Now at the interface, this is exactly where water is about to evaporate. So actually, before we even do that, hold on. Concentration of some kind of gas component usually is P over, or P up, partial pressure of that gas over RT. So we're going to be using this to help us out finding the other one. So concentration of water at the interface, at the interface really is just when that water is exactly about to evaporate. So that would mean that would be the pressure of water, the vapor pressure of water at that temperature over the ideal gas constant times the temperature of that water. That's the concentration at the interface. We can calculate all these quantities. We might have to use the Antoine equation for the pressure here, but regardless, we can still calculate that now. The concentration of water at the bulk is simply just the mole fraction of water times the overall concentration, which that would be mole fraction of water times the overall pressure of that system, which is just 1 atm, or atmospheric pressure, times the ideal gas constant times the temperature of the air, which we're given. So that takes care of those two. The next one, we have to do some really, really interesting stuff. So with the convective mass transfer coefficient, remember we were given this relation between the Nusselt number, the Reynolds number, and the Prandtl number. So with this, we can use the heat and mass transfer analogy to convert between some dimensionless numbers. So first conversion, this SH here, that replaces the Nusselt number, which equals 0.6 times the Reynolds number, because the Reynolds number is consistent for both heat and mass transfer. And the Prandtl number switches out with the Schmidt number. These two are equivalent statements because mass transfer and heat transfer have the same profiles for their types of transfer, which is very, very interesting. And you don't have to do mass transfer experiments. You save so much time. Anyway, the first step we're going to do with these equations, we're going to divide the SH over the Nusselt, or SH over the Nusselt number equals 0.6 RE 1/2 over the same thing, multiplied by the Prandtl number over 1/3 and Schmidt number over 1/3. So these guys cancel. They're gone now. And that yields us with convective mass transfer coefficient times, or the convective mass transfer coefficient times the thermal conductivity over the diffusion coefficient times the heat transfer coefficient equals Schmidt number over the Prandtl number to the 1/3. Now, second step here, Lewis number, which we were given earlier, equals the Schmidt number over the Prandtl number. Now with this guy equals viscosity over density times diffusion coefficient over viscosity, density, heat capacity over density and thermal conductivity, which this yields us with thermal conductivity over density, heat capacity, diffusion coefficient. which yields us that the thermal conductivity equals density, heat capacity, diffusion coefficient times the Lewis number. Now for step 3 here, we can actually shove these two together, so shove 2 into the first one. This gives us with Kc over diffusion coefficient times heat transfer coefficient times the density, heat capacity, diffusion coefficient, Lewis number equals the Lewis number to the 1/3, which is this term here. And this yields us, once the diffusion coefficients cancel out, that the convective mass transfer coefficient equals the Lewis number to the negative 2/3 times the heat transfer coefficient, all divided by the density times the heat capacity. So this takes care of our Kc now as well. For the last part, I need to get out a new piece of paper really quick. So for step 12, now we need to relate the mass average and the overall mass flow rate. So we're given a few quantities to do this. So first, we're given our mass flow rate of air. So with mass flow rate of air, area times the mass flow rate of air equals the volumetric flow rate times its density, which that equals the area velocity, which this is that 5 meters per second, times pressure, then the M average, or average molecular weight over RT. Now this gives us M average. So with M average, or average molecular weight, equals mass flow rate of water vapor plus the mass flow rate of air over mass flow rate of water times the molecular weight of water plus mass flow rate of air over the molecular weight of air. With this quantity, that ends up leading to that the mass flow rate of air equals the mole fraction of water times the overall mass flow rate over the molecular weight average times the molecular weight of water. Now that we know that, we can derive a few more statements. Actually, before even we had that, we've got the overall mass flow rate has to equal the air plus the water. Now with that, we can transform that equation before that. The mass flow rate of water equals mole fraction of water times molecular weight of water over the molecular weight average. Then plus those two quantities there, because we're simply just replacing this guy with this guy. And now finally, we can relate GW once more. Alrighty, so that takes care of G as well as the molecular weight average. So with all of that, we can actually write out the final set of differential equations with all known values. So our final set here would be, we'll start with what we derived first. So change temperature of air over position equals that surface area to volume ratio over mass flow rate of water times the heat capacity, heat transfer coefficient, TA minus TW minus lambda Kc CWI minus concentration of water infinity. Second differential equation was for air. Oh wait, this is for water. I'm sorry, everyone. And for air, we've got area over overall mass flow rate times the heat capacity of air. This is for water, I forgot that. Times the heat transfer coefficient, and then the difference in temperatures. And finally, now we've got our material balance. With our material balance, we get the mole fraction of water related to position, which that would be the negative surface area to volume ratio times the molecular weight average over the overall mass flow rate. You got Kc, and then we use the difference in water concentration. Alrighty, and we also solved for the 5 unknown quantities, which we've got the concentration of water at the interface, concentration of water at the bulk, the convective mass transfer coefficient, average molecular weight, as well as the overall flow rate. So with that, thank you very much, and please have a good rest of your day.